multimeter, test a photodiode and test the LED and photodiode in combination.
Let us get started by learning about the digital multimeter. Digital multimeter is used to compute various electrical quantities like voltage, current, capacitance, resistance, values of diode and impedance, etc. A digital multimeter is a diagnostic tool used by technicians and electrical engineers and combines the features of a voltmeter, ammeter, and ohm meter. It typically includes probes, clamps, or leads which are inserted into inputs on the instrument and then connected to the device under test to make a measurement. Before learning about the photodiode, let us first understand the PN junction diode. A PN junction diode is a piece of silicon that has two terminals. One of the terminals is doped with P-type material and the other with N-type material. The PN junction is the basic element for semiconductor diodes. A semiconductor diode facilitates the flow of electrons completely in one direction only, which is the main function of PN junction diode or semiconductor diode. It can also be used as a rectifier. PN junction has two bias conditions. They are forward and reverse bias. In forward bias, PN is connected to positive terminal of power supply and N end is negative. Forward bias will reduce the depletion layer and allow the current flow through the junction. In reverse bias, P end is connected to the negative terminal of power supply and N end is positive. Reverse bias will enhance the depletion layer and block the current flow. PN junction diode in the reverse biased configuration is sensitive to light from a range between 400 nm to 1000 nm, which includes visible light. Therefore, it can be used as a photodiode. It can also be used as a solar cell. PN junction forward bias condition is used in all LED lighting applications. The voltage across the PN junction bias is used to create temperature sensors and reference voltages. A photodiode is one type of light detector used to convert the light into current or voltage based on the mode of operation of the device. It is very sensitive to light, hence when light falls on the diode, it easily changes light into an electric current. For example, the solar cell is a photodiode that converts solar energy into electric energy, though solar cell works only in bright light. Some photodiodes will look like a light-emitting diode. It's time to test your understanding. Your first task is to test an LED using a digital multimeter. To perform this task, you need a digital multimeter with diode testing and an LED. Basic multimeters measure are just amps, volts and ohms. To test LED lights, select a multimeter with the diode setting. Connect the red and black test leads to the outlets on the front of the multimeter. The red lead is the positive charge. The black lead is the negative and should be plugged into the input labeled COM. Connect the black probe to the cathode and the red probe to the anode. Touch the black probe to the cathode end of the LED, which is usually the shorter prong. Next, touch the red probe to the anode, which should be the longer prong. Be sure to connect the black probe before the red probe, as the reverse might not give you an accurate reading. Turn the dial on the front of multimeter clockwise to move it away from the off position. Your second task is to test a photodiode. You need a digital multimeter with diode testing and a photodiode for this task. Connect the photodiode to the multimeter similar to testing a normal diode or an LED by referring to the diagram shown. Take precautions in connecting the probes as well as the terminals of the photodiode. Your final task is to test LED and photodiode in combination. To perform this task, you need a digital multimeter or millivoltmeter, photodiode, LED with a suitable current control resistor, 6 volts battery or DC power supply, and a control switch. The photodiode can be tested for actual operation by arranging the light from an LED to fall on its sensing side. Connect the LED and photodiode in a circuit as shown. Switch on the circuit and verify the deflection or reading on the meter.
We have reached the end of this session on test an LED and a photodiode to verify the photo emitting effect and light sensitivity. By now, you should be able to know the digital multimeter, describe a photodiode, and explain the procedure to test an LED using a digital multimeter, test a photodiode, and test LED and photodiode in combination. In this session, we will learn how to test a photovoltaic cell or PV cell for different illumination levels and verify photovoltaic property. At the end of this session, you will be able to know the photovoltaic cell and explain how to test a photovoltaic cell.
A solar cell or photovoltaic cell is an electrical device that converts the energy of light directly into electricity by the photovoltaic effect. It is a form of photoelectric cell which, when exposed to light, can generate and support an electric current without being attached to any external voltage source. This method converts the sun's energy into electricity. A single solar PV cell will have an output of approximately 0.5 volts and current of few milliamps, which depends on various factors such as type and quality of the cell, solar irradiation, incident angle of solar irradiation, shadow spectrum of incident radiation, etc. They are grouped to get higher outputs. The electricity generated by the photovoltaic effect can be either used directly or can be stored in batteries or can directly fed into an electric utilities grid system. The energy stored in the battery can be used to operate any electrical device. If the device operates on DC, then it can be directly connected to the output load. If the device operates on AC, then an inverter is required to convert DC into AC. Main materials used to develop solar cells are silicon, cadmium tellurides, etc. A photovoltaic cell is an energy harvesting technology that converts solar energy into useful electricity through a process called the photovoltaic effect. There are several different types of PV cells which all use semiconductors to interact with incoming photons from the sun in order to generate an electric current. A photovoltaic cell is comprised of many layers of materials, each with a specific purpose. The most important layer of a photovoltaic cell is the specially treated semiconductor layer. It is comprised of two distinct layers, P-type and N-type, and is what actually converts the sun's energy into useful electricity through a process called the photovoltaic effect. Let us learn how photovoltaic cell works. On either side of the semiconductor is a layer of conducting material which collects the electricity produced. Note that the backside or shaded side of the cell can afford to be completely covered in the conductor, whereas the front or illuminated side must use the conductors sparingly to avoid blocking too much of the sun's radiation from reaching the semiconductor. The final layer, which is applied only to the illuminated side of the cell, is the anti-reflection coating. Since all semiconductors are naturally reflective, reflection loss can be significant. The solution is to use one or several layers of an anti-reflection coating to reduce the amount of solar radiation that is reflected off the surface of the cell. Photovoltaic cell can be manufactured in a variety of ways and from many different materials. The most common material for commercial solar cell construction is silicon, but others include gallium arsenide, cadmium telluride, and copper indium gallium selenide. Solar cells can be constructed from brittle crystalline structures or as flexible thin film cells. Crystalline solar cells can be further classified into two categories. They are monocrystalline and polycrystalline. Monocrystalline PV cells are comprised of a uniform or single crystal lattice, whereas polycrystalline cells contain different or varied crystal structures. Now that you are familiar about the photovoltaic cell, let us do a task to test your understanding. To perform this task, you need a digital multimeter or millivoltmeter, a photovoltaic cell, 3.5 watts, 0.5 volts, 7 ampere, 4 numbers, ohm, 5 watt resistor, sunlight, and alternative light source with illumination control. Now, place the solar cells in direct sunlight and use a multimeter that measures both voltage and ampere.
We have reached the end of this session on test a photovoltaic cell or PV cell for different illumination levels and verify photovoltaic property. By now, you should be able to know the photovoltaic cell and explain how to test a photovoltaic cell. In this session, we will learn how to plot IV curve for photovoltaic cell based on the illumination at constant temperature. At the end of this session, you will be able to know the IV curve for photovoltaic cell, describe the equipment solar simulator, explain the characteristics of solar cell, detail on the IV characteristics of PV cell for variation in the illumination and the load.
Let us get started with the IV curve of photovoltaic cell. The solar cell IV characteristics curves shows the current and voltage IV characteristics of a particular photovoltaic cell, module or array. It gives a detailed description of its solar energy conversion ability and efficiency. Knowing the electrical IV characteristics, more importantly P max of a solar cell or panel, is critical in determining the device's output performance and solar efficiency. Photovoltaic solar cells convert the sun's radiant light directly into electricity. The graph shows the current voltage characteristics of a typical silicon PV cell operating under normal conditions. The power delivered by a single solar cell or panel is the product of its output current and voltage. If the multiplication is done point to point for all voltage from short circuit to open circuit conditions, the power curve is obtained for a given radiation level. When the solar cell open circuited is not connected to any load, the current will be at its minimum, 0, and the voltage across the cell and its maximum, known as the solar cell open circuit voltage or VOC. At the other extreme, when the solar cell is short circuited, that is, the positive and negative leads connected together, the voltage across the cell is at its minimum, 0, but the current flowing out of the cell reaches its maximum, known as the solar cell short circuit current or ISC. Here is the IV curve of solar panel. PV panels can be wired or connected together in either series or parallel combination or both to increase the voltage or current capacity of the solar array. If the array panels are connected together in a series combination, then the voltage increases, and if connected together in parallel, then the current increases. The electrical power in watts generated by these different photovoltaic combinations will still be the product of the voltage times the current. However, the solar panels are connected together. The upper right hand corner will always be the maximum power point of the array. A solar simulator is a light source that has specific quantifiable similarities to natural sunlight, namely in its spectral distribution and intensity. It may also be referred to as an artificial sun or sunlight simulator. The solar simulator has special air mass filters and lamps to simulate the sun's solar spectrum. The purpose of a solar simulator is to provide a consistent, controllable source of illumination in a laboratory environment for testing any materials or processes that are photosensitive. It is time to test your understanding. To perform the task, you need solar energy meter and the solar simulator equipment. Your first task is to understand the lab equipment solar simulator. Study the lab equipment available in shop floor to learn the IV characteristics of PV cell. Go through the manual supplied along with the equipment to know the different controls used in it and their usage. Learn the do's and don'ts. Get familiar with simulation with solar lights properties. Remember, technical circuit inside and its functioning not required for your study of PV cell. Common features of this solar simulator should be: to simulate the sun, set of lamps are used as the source of light. To simulate the sun for its heat radiation, an electrical hot plate is used. To simulate east-west movement of the sun, the lamps are provided individual control. To simulate variation in solar irradiation, the intensity of the lamps need to be controlled. To simulate variation in temperature, the heat generated by hot plate needs to be controlled. The location of the solar PV cell is to be over the hot plate facing the lamps. A variable resistive load is required across the terminals of the solar PV cell to indicate actual load conditions. A set of digital, preferably voltmeter and ammeter, are essential on front side. Control of intensity and heat should be independent. Your second task is to study voltage, current and characteristics of solar cell. To perform this task, you need a solar simulation lab. Connect the solar simulator equipment to mains power supply and switch on. Set both the intensity controlled rotary switch of lamps at maximum position to get the full intensity. Measure the intensity using solar energy meter and record the observed value. Set the variable resistor load provided at high to simulate no load condition. Measure and record the voltage and current of solar cell at no load condition on display. The voltage displayed on voltmeter is open circuit voltage. Vary the load progressively downwards. Simultaneously measure the VI readings and record. The minimum position of load indicates the short circuit across the PV cell and hence the current will be highest. It is the short circuit current of solar PV cell. Plot the path of curve for recorded values of V and I to get the IV curve of the solar PV cell at fixed intensity. Your final task is to study the voltage, current, characteristics of solar cell with variation of light intensity and varying load conditions. You need solar simulator equipment to perform this task. Connect the solar simulator equipment to mains power supply and switch on. Set both the intensity control rotary switch of lamps at maximum position to get the full intensity. Measure the intensity using solar energy meter and record the observed value. Set the variable resistor load provided at high to simulate no load condition. Measure and record the voltage and current of solar cell at no load condition on display. The voltage displayed on voltmeter is open circuit voltage. Vary the load progressively downwards. Simultaneously measure the VI readings and record the observations. The minimum position of load indicates the short circuit across the PV cell and hence the current will be highest. It is the short circuit current of solar PV cell. Repeat the above with reduced intensity at different levels. Plot a graph for each set of observations to get the IV curves of the solar PV cell.
We have reached the end of this session on plot IV curve for photovoltaic cell based on the illumination at constant temperature. By now, you should be able to know the IV curve for photovoltaic cell, describe the equipment solar simulator, explain the characteristics of solar cell, detail on the IV characteristics of PV cell for variation in the illumination and the load. In this session, we will learn how to plot IV curve for photovoltaic cell based on temperature at constant illumination. At the end of this session, you will be able to know the standard test conditions or STC, describe the equipment solar simulator, explain the characteristics of solar cell of a PV module, and detail on the IV characteristics of PV cell for variation in temperature on cell.
Let us learn about the standard test conditions of a PV module. Every manufacturer tests their modules under standard test conditions, which is a set of rules to follow at manufacturing industry. These rules allow consumers and solar designers to compare panels. Normal STC includes solar cell temperature of 25 degrees Celsius, solar irradiance of 1000 watt per square meter, and the air mass 1 or 1.5. The air mass is the path length which light takes through the atmosphere normalized to the shortest possible path length. The air mass quantifies the reduction in the power of light as it passes through the atmosphere and is absorbed by air and dust. Air mass is the measure of how far light travels through the Earth's atmosphere. One air mass or AM1 is the thickness of the Earth's atmosphere. AM 1.5 is almost universal when characterizing terrestrial power generating panels. A solar simulator is a light source that has specific quantifiable similarities to natural sunlight, namely in its spectral distribution and intensity. It may also be referred to as an artificial sun or sunlight simulator. The solar simulator has special air mass filters and lamps to simulate the sun's solar spectrum. The purpose of a solar simulator is to provide a consistent, controllable source of illumination in a laboratory environment for testing any materials or processes that are photosensitive. The solar cell IV characteristics curves shows the current and voltage IV characteristics of a particular photovoltaic cell, module or array. It gives a detailed description of its solar energy conversion ability and efficiency. Knowing the electrical IV characteristics, more importantly P max of a solar cell or panel, is critical in determining the device's output performance and solar efficiency. Photovoltaic solar cells convert the sun's radiant light directly into electricity. The graph shows the current voltage characteristics of a typical silicon PV cell operating under normal conditions. The power delivered by a single solar cell or panel is the product of its output current and voltage. If the multiplication is done point to point for all voltage from short circuit to open circuit conditions, the power curve is obtained for a given radiation level. When the solar cell open circuited is not connected to any load, the current will be at its minimum, 0, and the voltage across the cell and its maximum, known as the solar cell open circuit voltage or VOC. At the other extreme, when the solar cell is short circuited, that is, the positive and negative leads connected together, the voltage across the cell is at its minimum. 0, but the current flowing out of the cell reaches its maximum, known as the solar cell short circuit current or ISC. Here is the IV curve of solar panel. PV panels can be wired or connected together in either series or parallel combination or both to increase the voltage or current capacity of the solar array. If the array panels are connected together in a series combination, then the voltage increases, and if connected together in parallel, then the current increases. The electrical power in watts generated by these different photovoltaic combinations will still be the product of the voltage times the current. However, the solar panels are connected together, the upper right hand corner will always be the maximum power point of the array. Now, let us do a task to test your understanding on the concepts learned. You need solar simulator equipment, thermometer, and solar energy meter to perform this task. Your task is to study the IV curve for 3 different temperatures on solar PV cell with constant intensity. Connect the solar simulator equipment to mains power supply and switch on. Set both the intensity control rotary switch of lamps at maximum position to get the full intensity. Measure the intensity using solar energy meter and record the observed value. Measure the room temperature. Record the observations. Use the temperature controller and set a value little above room temperature. Set the potentiometer to maximum to get no load condition. Measure the voltage and current of solar cell at no load condition on display. Vary the potentiometer towards minimum. Measure the voltage and current of solar cell at full load condition on display. Record the observations. Repeat the steps above with temperature at still higher set value. Record the observations. Draw the graph for normal, higher, and much higher temperature values and compare. Record the observations.
We have reached the end of this session on plot IV curve for photovoltaic cell based on temperature at constant illumination. By now, you should be able to know the standard test conditions or STC, describe the equipment solar simulator, explain the characteristics of solar cell of a PV module, and detail on the IV characteristics of PV cell for variation in temperature on cell. In this session, we will learn how to test photovoltaic cell in sunlight at various angles of inclination and direction. At the end of this session, you will be able to know the best direction for solar panels to face, explain the specific information on installation in fixed or variable angle of inclination of solar panels, and describe the working of PV cell or panel in sunlight at different angles and directions.
Let us get started by knowing the best direction for the solar panel to face. The traditional advice is to position solar panels to be north facing or south facing, depending on the location in the southern or northern hemisphere respectively. This is because for those living in the northern hemisphere, the sun is always along the southern part of the sky as we complete our yearly orbit around it. Similarly, for those living in the southern hemisphere, the sun is always along the northern part of the sky as we complete our yearly orbit around it. Thus, the general best practice to date has always been to position solar panels facing south for places in northern hemisphere in order to capture the maximum amount of sunlight overall. Facing of the panel is towards south for locations in northern hemisphere, north for locations in southern hemisphere, and flat on equator. Generally, it's common knowledge in the solar industry that these south-facing panels should be tilted between a 30 and 40 degree angle. But this angle varies and is just about equal to the latitude of your home. how far north you are in relation to the equator. The reasoning behind this angle specificity is to ensure sunlight hits panels at a perpendicular angle which produces the most energy. Now, let us learn how to adjust the tilt angles in solar panel by providing proper angle of inclination. The sun's path changes throughout the year. The days are longer during the summer, which means we get the most sunlight because of the sun's summer path. Hence, the solar panels are able to produce the most energy during the summer, and during the winter, the sun's rays are less direct because its path has changed. This is important because it may affect the slope of the solar panels. If we can adjust the tilt of the solar panels, even manually, they will be significantly more efficient. If this applies in a site, consider increasing the tilt of the solar panels by 15 degrees during the winter. During summer months, decrease the original tilt by 15 degrees. This results in summer angle and winter angle, increasing the output power. Adjusting the inclination angle for changing or setting the seasonal angle is 22 days from the equinoxes, and the optimum value of tilt angle adjustment from the site latitude is in between 23 to 25 degrees for maximizing the annual energy collection. If your latitude is between 25 degrees and 50 degrees, then the best tilt angle for summer is the latitude times 0.93 minus 21 degrees. The best tilt angle for winter is the latitude times 0.875 plus 19.2 degrees. The seasons are winter from December to February, spring from March to May, summer from June to August, and autumn from September to November. Now let us do few tasks to test your understanding. You need solar PV cell, voltmeter, ammeter, 5 ohm resistor, magnetic compass, spirit level, and clinometer. Your first task is to study the solar power generated in different directions. Connect the given components as shown in circuit. The light sensor of the solar energy meter should face in the same direction as the solar PV cell in each case of testing. Place the solar PV cell in sunlight. Locate the north pole using the magnetic compass. Keep the solar PV cell facing the north pole. Record the readings on voltmeter and ammeter and solar irradiation intensity. Rotate the facing of the solar PV cell by 90 degrees from north clockwise. Record the readings on voltmeter and ammeter. Continue to rotate the facing of the solar PV cell by 90 degrees from earlier position clockwise. Record the readings on voltmeter and ammeter. Continue to rotate the facing of the solar PV cell by 90 degrees from earlier position clockwise. Record the readings on voltmeter and ammeter. Compare the results. Your next task is to study the solar power generated in different angle of inclinations. The light sensor of the solar energy meter should face in the same direction as the solar PV cell in each case of testing. At any point of experiment, mind that no shadow falls on the PV cell. Connect the given components as shown in circuit. Place the solar PV cell in sunlight at flat surface. If mounted on adjustable plane, allowing different inclinations, more suitable, otherwise manually done. Check the spirit level shows flat surface parallel to the ground. Measure the angle using clinometer and confirm it shows 0 degrees. Keep the solar PV cell facing the south. Record the readings on voltmeter and ammeter and solar irradiation intensity. Lift the facing of the solar PV cell by steps of 5 degree from 0 degree. Record the readings on voltmeter and ammeter. Continue to change the angle of facing of the solar PV cell from earlier position towards south. Record the readings on voltmeter and ammeter. Repeat the above for some more angles. Compare the results. The angle that gives maximum solar power is the tilt angle for given location.
We have reached the end of this session on test photovoltaic cell in sunlight at various angles of inclination and direction. By now, you should be able to know the best direction for solar panels to face. Explain the specific information on installation in fixed or variable angle of inclination of solar panels and describe the working of PV cell or panel in sunlight at different angles and directions. In this session, we will learn how to record specification of different solar panels and compare specifications to select a panel. At the end of this session, you will be able to know the specifications of solar panels, study the specification chart for solar panel and compare the specifications of different rated solar panels.
Now let us learn about the typical specifications of a solar panel. The typical specifications include test certificate, manufacturer's test certificate and quality standard. Backside of the solar panel. In a designer approved single line diagram, these points are already considered and made available in SLD and part list. The technician can verify as far as possible the panels issued for installation or drawn from store shall have the information correct. Let us see the other features to be verified in the solar panel. ASTM is the standard spectrum or the type of light that shines on a solar panel. Production tolerance. Manufacturers often assign an allowable tolerance of plus or minus 5% to the module's rating. Hence, a 100 watt solar can be either 95 or 105 watts. Temperature. Higher cell temperature than the 25 degrees Celsius will decrease efficiency. Roof-mounted arrays will show temperatures in the 50 degrees to 75 degrees Celsius range, which is 2 to 3 times the STC rating. Dirt and dust. These block sunlight reaching to cells. Eventually, panels get dirty until the next rainfall or hose spray. This can account for about a 2% on average loss. Wiring losses. DC wiring accounts for power losses due to the resistance of the wiring system. We usually design for a 2% wire loss. Inverter losses. On average, over a day, this is about 90%. Success in the solar industry starts with testing and certification. To thrive in the solar energy sector, manufacturers and retailers need to ensure that their products meet established quality and performance standards. This means demonstrating that their PV modules are robust and able to consistently deliver the guaranteed rated power reliably even under more severe climatic conditions. They must also be safe and durable, ensuring the system's high yield over the long term and still need to be commercially viable. Industries have developed testing services that address market needs and enable users to meet their goals. At ISO 17025 accredited laboratories around the globe, the manufacturers test and certify PV modules according to national and international standards, including IEC 61215 and IEC 61730. Besides this, they offer testing under special as well as more severe conditions, performance characterization, and energy yield testing, just to name a few. International standards such as EN, IEC, ANSI keep abreast of changes and harmonization that affect market access for PV modules. Few certification services consist of the following process steps. Laboratory tests on samples for a module family or type, recurring factory inspection, certificate and TUV Greenland Test Mark, Certificate of Conformity COC or Declarations for Individual Markets and Bankability Reports. Quality assurance measures for PV modules include PID, Potential Induced Degradation, electroluminescence and IR imaging, pre or post shipment inspections, aging of micro cracks, and LID test, light induced degradation. Stress tests include fire tests, corrosion tests, outdoor long-term tests in different climate zones, transport and environmental simulation on PV module shipping units, sand abrasion tests, and snow load testing. Added value services are PV plus benchmark, qualification plus certification, and energy yield testing under actual climate conditions in relevant target markets. BIPV qualification of building integrated PV include risk analysis, roof integration, facade integrated systems, hail testing, and snow load testing. Measurement of area of the cells and compare with the module area in data sheet. Every solar panel is made up of individual solar photovoltaic PV cells. PV cells come in a standard size of 156 mm by 156 mm. For example, if the area of one PV cell is 243.36 cm square, area of 60 PV cells is equal to 14,601.6 cm square. Area of a solar PV panel of 60 cells is equal to 16,335 cm square. The average size of solar panels used in a rooftop solar installation is approximately 165 cm times 99 cm. The length can go up to 182.88 cm. Most solar panels for rooftop solar installations are made up of 60 solar cells, while the standard for commercial solar installations is 72 cells and can go up to 98 cells or more. The number of solar cells on one panel is directly related to its length. 72 cell commercial solar panels are approximately 33 cm longer than 60 cell residential panels. If you install a 6 kW system with 20 average sized panels, your system will likely measure approximately 8.23 meter wide by 3.96 meter long is equal to 32.59 meter square. Testing using multimeter is easier. Test the solar panel for voltage across the output terminals. For this, first keep the solar panel in sunlight. Set your multimeter to DC volts setting. Touch the positive lead to the panel's positive wire and negative lead to the negative wire of the solar panel. If meter reads selected range is low, rotate the dial to increase the range. Note the voltage displayed and compare it with VOC rating given on the back of the panel in the label. It should be close to VOC. If it reads, so then the given solar panel is good. If it is not, then there is a problem with the given panel. In such a case, go back and check the connections of solar cells strings for any break or any crack in the solar cells. If you find anything like that, we can't repair ourselves. It should be sent to manufacturer for repair or replacement. Series connection. Solar PV panels connected in series are called string. Strings connected in parallel make an array. For a series connection, connect positive terminal of one panel to the negative terminal of other panel and so on. Then positive terminal of first panel is the positive terminal of the series path and negative terminal of last panel is negative terminal of the series path. The voltage of series connected panels is addition of individual panel voltage. The current path is single and hence series connections current is equal to current of a single panel. Conditions are all panels in series path must be of same ratings and specifications. No mixing of ratings is allowed. Here is the calculation method for series connection. For a parallel connection, connect positive terminal of all panels together and connect all negative terminals together. Terminals taken out from any one of the panel gives positive and negative terminals of the combination. Here is the calculation method for parallel connection. Let us now test your understanding on the concepts learned. You need 5 watts, 10 watts, 40 watts and 250 watts polycrystalline modules to perform this task. The task is to compare the specifications of different solar panels. Study the specification chart provided on each panel and fill up the table. Compare and comment on their suitability for your use.
We have reached the end of this session on record specification of different solar panels and compare specifications to select a panel. By now, you should be able to know the specifications of solar panels, study the specification chart for solar panel and compare the specifications of different rated solar panels. In this session, we will learn how to connect suitably rated wires in the terminal box of a solar panel and connect end terminals using MC4 connectors. At the end of this session, you will be able to know the terminal wires and MC4 connectors, explain the types of MC4 connectors, know the junction box and list the steps to connect MC4 connector to the DC cable or wires.
Let us learn about the MC4 connectors. The MC4 system consists of a plug and socket design. The plugs and sockets are inside plastic shells that appear to be the opposite gender. The plug is inside a cylindrical shell that looks like a female connector but is referred to as male, and the socket is inside a square probe that looks male but is electrically female. The female connector has 2 plastic fingers that have to be pressed toward the central probe slightly to insert into holes in the front of the male connector. When the two are pushed together, the fingers slide down the holes until they reach a notch in the side of the male connector where they pop outward to lock the two together. For a proper seal, MC4s must be used with cable of the correct diameter. The cable is normally double insulated, insulation plus black sheath, and UV resistant. Most cables deteriorate if used outdoors without protection from sunlight. Connectors are typically attached by crimping, though soldering is also possible. The MC4 connector is rated at 20 amperes and 600 volts maximum, depending on the conductor size used. Standards allow 1000 volt versions. A general MC4 connector specification includes manufacturer name, rated for say 30 amps max, the connector itself, not the wire, rated for say 1000 volts max, and rated temperature range say minus 40 degrees Celsius to plus 90 degrees Celsius, minus 40 Fahrenheit to 194 Fahrenheit. Due to the locking mechanism of the MC4 connectors, they will not come unplugged and are well suited for outdoor environments. The connectors can be separated, but it requires a special MC4 unlocking tool. In a series connection, the modules are wired together by connecting the positive lead on one module to the negative lead on another module. The male connector will snap directly into the female connector. This increases the voltage of the circuit. If the modules are rated for 18 volts at maximum power VMP, then two of them connected in series will measure 36 VMP. If 3 modules are in series, the total VMP would be 54 volts. The current at max power IMP will be constant when wiring a series circuit. A device called a PV combiner box is used for paralleling more than 2 modules or paralleling strings of modules. The combiner box will be performing the same function of the multi-branch connectors but for more than 2 panels. The total number of modules that can be combined will depend upon the electrical rating and physical size of the combiner box and also on the PV design. Further, the technician should know how to select and use MC4 extension cables. Each wire located inside a 4 mm cable works as a conductor, and the cable is comprised of multiple such conductors. Solar wires are made from a sturdy material such as copper or aluminum. These materials provide reliable connectivity and the ability to transfer electricity from the solar panels to the home. Let us learn the steps to connect MC4 connector to the DC cable. Requirements are male and female MC4 connectors, 4 mm solar cable, wire crimps, and wire strippers. Set up the connectors. Mark the distance and decide on the length of the cable so as to join all MC4 connectors together. Crimp male connector. Take the cable and put a small bend on it to ensure better surface contact within the crimp. Strip the cable insulation by a small amount in order to expose the wire for crimping. Start by passing the screw nut over your metal crimp and then make sure the plastic housing has a non-return clip inside it. If you didn't put the nut on the cable first, you won't be able to get the plastic housing off. Secure rubber washer. The seal washer, made of rubber, is flush at the end of the cable, requires the nut to be tightened closely. This gives a solid grip for a 4 mm solar cable. Otherwise, the connector may spin around the cable and damage the connection. Insert 4 mm cable. After crimping the 4 mm solar cable right, push in the connector till a click sound is heard, which indicates it is secured safely. Then lock the cable in the plastic housing. This completes the connectivity for the male connector. Crimp female connector. Crimp the female connector the same way as it was done for the male connector. Connect the cable. At this stage, you only have to insert the cable. Pass the screw nut over the cable and check the rubber washer again. Then you need to push the crimped cable into the female housing. You should hear a click sound here as well to know it is locked it in place. This completes the connectivity for the female connector. Test connectivity. The final stage of the connecting process is to test the connectivity. Test the MC4 connectors exclusively before connecting them to the main solar panels or the charge controller in order to verify everything is working properly. An array junction box is used to connect the photovoltaic strings in parallel. The combined DC power is fed to the photovoltaic inverter. It includes photovoltaic string protection, overvoltage protection, and a DC output switch isolator. The AJB can be customized for different configurations based on the number of strings of solar panel modules used in the layout. AJB have the following components: enclosure, PV fuses, surge protection device, DC disconnect or isolator, and cable glands or connectors. These are the protection devices in an AJB. It is time to test your understanding. To perform the task, you need MC4 connectors, DC cables, wires, tools kit with crimping tool and soldering iron, 25 watts. Your task is to connect wires or DC cables to MC4 connectors. DC volt more than 70 volts prove very dangerous. Once solar panels are exposed to sunlight, they start generating DC volt. Study the pictures to familiarize with assembly parts of MC4 connectors. Practice connecting the MC4 connectors on red and black DC cables suitably selected. Practice extension of solar panel output wires as per requirement. Where panel terminal junction box do not have OEM output cables, select suitable color coded cables and on one end MC4 connectors. On another end, solder to the relevant terminals on the panel junction box.
We have reached the end of this session on connect suitably rated wires in the terminal box of a solar panel and connect end terminals using MC4 connectors. By now, you should be able to know the terminal wires and MC4 connectors, explain the types of MC4 connectors, know the junction box and list the steps to connect MC4 connector to the DC cable or wires.
अरे गीता, तुम मेरे घर आई ये तो बहुत अच्छी बात है। वास्तव में मुझे इंटरनेट के बारे में कई महत्वपूर्ण बातों को समझने में तुम्हारी मदद की जरूरत है।
जरूर चाचा, मैं यहाँ आपकी मदद और मार्गदर्शन के लिए आई हूँ।
देखो गीता, जब मुझे ट्रेन से कहीं जाना होता है तो मुझे बहुत मुश्किल